Just to make sure, can everyone see my screen properly? If yes, be very kind to leave a little message in the chat box so I can be sure that everyone can see it. And we will be starting in about 3 minutes. We're just waiting for a few more people to join the webinar. Great, so I can hear that everyone can see my screen fine. So we'll get started in about a minute. We've got about 85 people so far, which is very exciting. All right, so let's get started on the presentation. So if you have any questions during the webinar, feel free to post them in the chat box. If the question is really important, I will address it right away. But if it's not so important, I will address it towards the end. But make sure to post your question so I have an idea of, about your understanding so far. So first of all, I'd like to thank Adele Green for organizing this webinar and eSynergy Solutions. Thanks for putting that together. Just to give a little bit of a background about who is speaking. So I'm a final year PhD at the University of Cambridge. I've been doing research in source code analysis, automated refactoring, type systems, and just programming languages in general. And very excited about what Java has to offer now because it gets a little bit closer to functional programming, and I will discuss that later in the webinar. I know a lot of you are from London, and I did my undergrad at Imperial College London, hopefully some of you as well. I've been involved with many programming language projects at Google in the Python team, at Oracle, working on the Java compiler. I'd recommend you guys read about the Oracle Java magazine if you're not aware of it yet. It's published every 2 months with a very interesting technical articles. So what are we going to cover today? There is a lot of material. Java 8 is huge upgrade to previous version of Java. Some people say it's the largest update to the language in its history. So I will get started with some motivation. Why should you actually care about Java 8, right? What does it bring to you as a developer or an architect? What should you incorporate that into your code base? Then next we'll discuss about a design pattern called behavior parameterization. So it's a very scientific name for something that's really useful, and Java 8 makes use of this pattern heavily, so we'll introduce that. We'll follow up with Lambda Expressions, which are the flagship feature that Java 8 brings. So we'll talk about what they are, what you can do with them, how they can improve your code. Then we'll go on with the next big Java 8 features, which is streams. And finally, we'll discuss about a new class called optional that might change how you deal with null pointer exceptions. And we'll conclude with default methods, which is an enhancement to interfaces in Java. So there's a lot to cover, and my goal is to give you an overview of all of them, but specifically shows you how you can improve your code base using those features. So let's get started. So you can find this information after the talk in a book I've been writing with Mario Fusco and Alan Mycroft. It's called Java 8 in Action, Lambdas, Streams, and Functional Style Programming. So if you want to go in more depth about the topics I'll cover, you can get this book. It's 400 pages, and there's a lot of material. So hopefully you'll find it interesting. So first of all, let's address the important question. Why should you care about Java 8 at all? What does it bring to you? So it turns out we are writing a lot of obscure code, right, on a day-to-day. So in this example, what we're trying to do is giving an inventory, so a list of apple. We would like to sort the list of apple based on the weight. In order to do this, we have to create this sort of comparator object that explains us how we can compare two apples. So here we provide an implementation for it. We implement the compare method, takes two apples, and then says, well, just take the property weight and compare it with the second property weight of the second apple. So there's a lot of boilerplate code involved to do this. In Java 8, the same problem can be solved in one line. So this is the green line here below, which says, well, given an inventory, just sort it, comparing with the weights of the apple. So our code now reads a lot closer to the problem statement, which is please sort the apples based on the weight. And this is one of the important things that Java 8 provides, will provide to you. It'll enable you to write code that reads closer to the problem statement. And do not worry about the syntax for now. I will explain that in a moment. So here's another use case about why you should care about Java 8. So I have a bunch of code here that processes a collection. So here we're saying, well, I like to loop through all a list of dishes, and I want to make sure that the current dish is below 400 calories. If yes, then we add it to an accumulator. Next, we create another accumulator and we say, well, you know what, I'd like to first sort all of those low-calorie dishes based on the calories. And then we'll iterate through the result and just extract the names and add it to the accumulator. So all of this code is kind of it's taking a lot of space. So you need to spend a lot of time to understand what it does. But if you look at the right side of my slide, you can see that what we do is actually filtering low-calorie dishes, then sorting them, and finally extracting the names. So that takes, just 10 seconds to understand what the code does if it's documented this way. And this is what Java 8 provides. It provides a new API to process collections in a more declarative way. So now, immediately, by looking at this code, we can see, well, take dishes, filter them, then sort them, and finally extract the names. So this new feature is called the Streams API, and I will discuss that later on in the webinar. So there's another side to the story. So as a developer, we care about Java 8, but what do language designers have to say about it? So it turns out the architectures that we use today have evolved completely compared to 10 years ago. These days, a computer has multi-cores, so several CPUs that can work in parallel. And we should make use of those architectures to write code that executes faster. Unfortunately, it's not so easy. So here's an analogy that I quite like. Let's say the task is to make coffee. If you have one assistant, it's fairly straightforward to ask the person to make coffee. You tell them, well, okay, just get the beans, put in the machine, get a cup, wait, and then my coffee is ready. What if you have to involve 4 assistants to make your coffee? Theoretically, the coffee could be made 4 times faster, right? Unfortunately, now you need to manage those 4 assistants. You need to figure out, okay, who is going to hold the cup of coffee, who is going to be in charge in using the machine, who's going to press the button, how do we synchronize all those people together? So it takes a lot more effort to figure that out. And this is the exact same problem we have with writing code that parallelizes. You know, writing sequential code that works on one CPU is straightforward. Unfortunately, when you involve multiple cores, it's a lot more difficult. So let's say you'd like to sum the numbers in an array. There might be transaction values. Then it's very easy to loop through them and accumulate the result. But how would you split this task if you had 4 CPUs available? Now suddenly we have to think about threads, we have to think about synchronization, we have to think about deadlocks. So it's a huge pain. And the language designers, you know, they understand this. They know about this. So Java 8 introduced features that make parallelization, you know, processing data in parallel a lot easier. So we can benefit finally from a multi-core architecture without having to write really complicated code that is difficult to maintain at the same time. So all of those features are driven from 3 concepts. The first one is stream processing. Second one is behavior parameterization. And finally, the idea of no shared mutable data. And I will explain each of them now. So what do we mean by stream processing? So this is actually a very old idea that is inspired from Unix commands. So you know you can pipeline commands in your shell. So you can say, first display me 2 files. So this is what the cat command does. Then we like to pipe this result into the command tr, which will replace capital letters into lowercase letters. Then we like to sort them. And finally, maybe truncate the result. So we can build this kind of nice pipeline of commands. And you may notice that, hey, actually, you know, we start displaying the first file and we're about to replace the letters. In the meantime, cat can process the second file. And we can already start buffering those lines and sort them. So all of these operations could be done in parallel. So this is what stream processing is about. It's about pipelining several programs together. So the output of one becomes the input of the next one. In Java 8, it looks this way. So here we take this code, which is written using the new Streams API, and we can pipeline a bunch of methods together. So here we say, well, given a list of dishes, we'll get a stream. So I will talk about that later. But first, we filter them with the dishes that are calories lower than 400. Then we sort them. And finally, we extract those names. So we've been able to pipe all those methods together. So that's the first concept that Java 8 is inspired from, stream processing. The second one is behavior parameterization. So I know it sounds complicated, but the general concept is easy to understand. So here's an example. Let's say you have a list of invoices and you have the invoice IDs. Well, you might want to sort this list of invoices in different ways. So you might want to take the first digits of the invoice number that might represent a date. So ideally, you like to tell the sort command, well, can you please use the first 6 digits that represent the date to sort them? Or You might want to sort the invoices based on a customer ID. So you have to extract that ID and tell the sort command, well, can you actually sort my invoices using the customer ID? So the sort command is parameterized with different ways of sorting. One is using the date, another one is using the customer ID. So this is really what behavior parameterization means. The sort command is parameterized with a behavior that we're trying to pass to that program. I will talk in more details about it in a moment, but for now, I'd like you to notice that this streams API in Java 8 heavily make use of this pattern. So we've got a filter method that says, well, I like to filter dishes that are of calories lower than 400. So we're parameterizing the behavior filter with this little piece of code that is passed as argument. And by the way, this is a Lambda expression, and we'll talk about it later. But this is the first use of Lambda expression of the webinar. So the next method is sorted and says, well, I'd like to sort based on the calories of the dish. So the behavior of the sorted method is also parameterized with its argument. And finally, we've got a map method that says, well, given a list of dishes, I like to extract the names, but we could also extract the calories, for example. In this case, we're passing a little bit of code, and this is called a method reference. It's also a new feature in Java 8, which we'll discuss later on. The third and final concept that Java 8 is driven from is the idea of no shared mutable data. So parallelization works nicely when the computations you want to do don't have to interfere. We don't have to synchronize on the result. And these streams of this pipeline of methods are not updating any data structures, any external data structures. So that's an important coding practice to keep in mind. All right, so now I'll give you a quick overview. Hopefully I've opened your appetite, and we'll go into more details to explain each of those features and concepts. So Java 8, what it does is provide you a concise way to pass behaviors. And this is driven from two features, one which is called Lambda Expressions, and the other one called method references. And we'll first look at these. The next one is a way to process data in parallel, and this feature is a new library called Streams API, which provides many operations such as filter, map, reduce, which you may have heard from other functional programming languages. Then we'll discuss about these. And another feature which we'll discuss is default methods, which allow you to have more flexible inheritance in Java. So let's get started with the basics. Behavior parameterization. So the goal with this pattern is to be able to abstract over behavior. So this pattern occurs frequently when, for example, you have to do something for every element in a list. Or you might want to do something else when you finish processing that list. Or if an error occurs, then you might want to do yet something else. So those are all behaviors that you like to execute in certain contexts. Why should you really care about this pattern? Well, it turns out you can really adapt for changing requirements if you embrace this idea of behavior parameterization. And the second reason why you should care about it is that the Java 8 Streams API makes heavily use of this pattern. So let's see how it works. Let's pretend for a moment that I am a farmer, and you are my customers, and I'd like to hire you to write a piece of software for me. So I have an inventory of apples, and I'm interested in knowing which apples are green in this inventory. So as a software engineer, we write our first piece of code, and we write a method, filter green apples, that takes a list of apples. We create an accumulator, which will be the result. We loop through every single apple in this inventory. We make sure that the color of an apple is green. If yes, then we add it, and so on until we've processed the whole list. So this is great. The farmer is happy because he can now find out about all green apples. But wait a minute. Now, the farmer changes the requirements a little bit and figures out, well, it's really awesome. You've written me a program that allows me to find green apples, but is there any way I can find out about red apples and maybe yellow apples? Well, as a good software engineer, you know, we figured that, okay, well, he's interested in different colors of apples, so we introduced a new parameter to the filter apples method. So here we say, well, it's going to take a color as parameter, and we can update the code so it figures out that, well, it's only filter apples based on the color argument. So if you can see the box at the bottom of the slide, this is one way to call the method. Filter apples by color, it takes the inventory, and then the green parameter or red parameter. Right, now the farmer is being a little bit annoying and figures out that, well, okay, well, filtering my inventory of apple by color is great, but you know, it'd be really awesome if I could find out about apples that are heavy because I can sell them for a higher price, and apples that are a bit lighter. So we like to filter apples based on their weight. Well, it turns out we've written the logic to do all this filtering. Unfortunately, we've got a method that only filters by colors. So what can we do? Well, it wouldn't be much effort to copy-paste this code and just change the color parameter into the weight parameter. And this is what this code does. We've introduced a weight parameter to the filter apples by weight method, and we've changed the condition, which is highlighted in red, to make sure that we only filter apples based on their weight and the given parameter. So if you look at the box at the bottom of the slide, this is how we could call this method. So I hope that now you can kind of figure out where this is going. So one problem that we have is that we actually have two methods that do very, very similar things. They are filtering a list of apples. Unfortunately, they use two different characteristics. One is weight and the other one is color. But you know, in software engineering, it's great to reuse code. So maybe there's a way we could merge those two methods into a single one. So we only have to maintain one method instead of two methods. So this is what this code does. And if you agree that it's ugly, then I completely agree with you. But bear with me. So here we're introducing a flag, a Boolean, that will decide whether we'd like to filter based on the color or based on the weight. And if you look at the box at the bottom of the slide, this is possible ways to call this method. Okay, but what if an apple had many, many characteristics? What if we'd be interested in the height of the apple? What would be interested in the shape of the apples? It would become a huge mess to combine all those different properties of an apple into a single method. So we need to take a step back. And ideally what we like to do is to model the selection criteria on an apple. And this is what we're trying to do here. So we're introducing an interface called apple predicate. And by the way, a predicate means essentially a function that takes an object and returns a Boolean. So this is why this interface is called an apple predicate. So it says, well, you need to implement one method that takes an apple as an argument, and then will return true or false. Using this interface, we are now able to declare different classes that model a different apple selection criteria. So for example, we could create the apple weight predicate class. It implements the test method and says, well, I just want to make sure that the apples are heavier than 150 grams. If you have a new requirement that comes in, all you have to do is implement this interface, and that's it. So for example, we could create another class, apple color predicate, and it says, well, I'm only interested in apples that are green. So now if the farmer comes with whatever fancy selection criteria he needs, we just need to declare a class that implements this interface. And because we've got access to an apple object, then we can write whatever selection criteria we need. And this pattern is sometimes called the strategy pattern as well. And the strategy design pattern is all about figuring out how to abstract away an algorithm. And here the algorithm is very simple. It's just a selection algorithm. So in UML, this would look like this, right? So we have this apple predicate interface, which models the algorithm, the selection process. And we've got multiple classes that are implementing this interface. we can now update our code in the following manners. So we introduce a new argument to the filter method that says, well, let's take an apple predicate. And we can now update our code to say, well, given apple, we will test if it matches the given predicate. And this is what this slide shows. We're calling the test method because it's passed the apple object that is from the inventory. So let's pause a little bit. Let's reflect on the benefits of what we've done so far. Actually, our code is much more flexible than our initial filter green apples method. We can really create any kinds of selection criteria on an apple, and we've been able to reuse of code for the filtering logic. We no longer have to maintain multiple methods declarations. So this is really great from a software engineering point of view. We can adapt for requirement changes. Unfortunately, you know, there's always a bad news. And the bad news here is that it's very verbose to declare all those classes that implement a selection criteria. So we have the right abstraction, but we don't have conciseness. So we need a better way to do this. We need a better way to create and pass those behaviors. So let's look at what we can do. How can we improve the story a little bit? Well, Java has this feature called anonymous classes that lets us declare and instantiate an object inline. So we don't have to declare a separate class and then instantiate an object. We can do all of this completely inline. So this is the syntax. And you know, here we're saying, well, I'd like to filter apples based on whether they're red. The second piece of code shows that, well, I might want to filter apples based on the weight, so heavier than 150 grams. And this is slightly better because we don't have to declare a class and instantiate it. We can do all of this directly inline. But this is still ugly. And here's a sixth attempt. And here we're introducing the new Java 8 feature called the lambdas. And it does the exact same code as the previous slide, but it's written slightly differently. So here we say, well, we like to filter the inventory of apples based on whether the color is red. And the second line shows that, well, we'd like to do the same thing, but based on the weight. So now our code is a little bit more concise. And do not worry about the syntax for now. We'll come to Lambda expression in a couple of minutes. But I just want you to notice that we've managed to reduce the code from about 4 or 5 lines to one line that is clearer. So our code is starting to look a lot closer to the problem statement. There's a further improvement that we can do to our code. Unfortunately, the filter method we wrote only worked on apples. But we can abstract this type as well. So here we're introducing a type parameter called t that says, well, given a list of t's and a predicate that works on this type as well, then we return a result that is a list of this type. And this is what the code shows. So now we can basically call the filter methods with different lists. We can pass a list of strings and say, well, I'd like to filter those strings that end with the extension JDK. Or we might have a list of numbers that we like to process and say, well, I only want to filter numbers that are even. Or we might even just use apples and say, well, I'd like to filter apples that are heavier than 150 grams. So we've done something truly amazing. We've managed to write code that adapts to requirement changes, is very concise, and works on any types of types. So this is the moral of the story. This is the moral of the story about this pattern called behavior parameterization. You can write code that is more flexible if you embrace this pattern. You can adapt for changes, and you can avoid code duplication. However, to encourage the use of this style, we need different features that Java 7 and before were not providing. We need the way to pass those behaviors in a concise way. And that's what Java 8 provides. And this feature is called Lambda Expressions. So here's a little summary of the discussion. So I quite like this diagram. So you can see that making use of value parameterization, so making use of arguments that takes an integer or strings, is very rigid and can be both concise and verbose. So verbose when we try to merge all those methods together. However, if you embrace more abstractions, so classes, anonymous classes, and lambdas, your code can become more flexible. However, they each have different trade-offs in terms of conciseness. And the sweet spot is lambda expressions. They are both concise and provide abstraction. So, I've given the motivation now for embracing behavior parameterization and for the need for a better feature to provide concise behaviors. So let's talk about lambda expressions. Here's the kind of scientific definition of what a lambda expression is, and we will drill down in the details in the next slides. So what is it? Well, it's a kind of anonymous function that can be passed around, and it doesn't have a name, but it has a list of parameters, a body, a return type, and possibly some exceptions that can be thrown. This is not a very useful definition, right? Because we now need to define what a function means, what anonymous means, what passing around means. So stay with me, and we will actually explain each of these in details. So this is what the syntax of a lambda expression looks like. You've got a list of parameters, which are the lambda parameters on the left-hand side. Then you've got a little piece of syntax, which is just an arrow, followed by the body of the lambda expression. So this is how you can recognize it in your code. So let's drill down in the definition a little bit to really understand what it is. So I said it's a kind of anonymous function. What does anonymous mean? Well, a lambda expression doesn't have a name. Methods have a name and classes have a name. Classes that don't have a name are called anonymous classes. And, well, methods that don't have a name are called lambda expressions. And the reason why we call them functions is because a lambda expression is not associated to a class like a method is. They can live on their own. So that's why we call them functions. The second part of the definition was that lambda expression can be passed around. What does this mean? Well, it means that a lambda expression can be passed as an argument to another method or stored inside a variable, just like an integer or an object. So they can be passed around. And finally, as I said, the lambda doesn't have a name, but it has a list of parameters, a body, a return type, and a list of exceptions, just like normal methods. And what's great about them is that they're really concise compared to anonymous classes. You don't have to write a lot of boilerplate code. As a piece of behavior, piece of code in a concise way. And by making use of them, you can code for changing requirements. So the great thing is that you no longer have to choose between abstraction and concision. Right, so let's look at a few examples of lambda expressions just to get a feel for it. So you can see in red is code written before Java 8, and in green is code written in Java 8. So in the red code, we show that, well, to sort a list, we need to create this comparator object, implement the compare method, provide those arguments, so it all looks very ugly. But using lambda expression, we can refactor this code into one line. So really, we don't really need to care about the compare method, and we don't even need to care about this comparator object. We just need to say, well, given two apples, please compare them using their weight. So that's the after code. And here are a bunch of examples of what lambda expressions look like for different use cases. So let's say we'd like to, in the first example, we take a list and we'd like to find out whether the list is empty. This is a way of representing a Boolean expression. Second use case is about creating objects. So here where we have a lambda expression that takes no parameters and just create an apple by initializing this constructor. We can also consume from an object. So this means that we don't need to return anything, but we can return void. So we're not returning an object, but we're consuming it. So here we're just saying, well, we just like to print the weight of the apple. We can also extract or select information from objects. So we have here a lambda expression that takes a string as argument and return its length. We can do other very nice things, for example, combining two values. So in this example, we have a lambda expression that takes two integers and multiplies them. Finally, as you can see in the previous example, we were taking two objects and showing how to compare them. So those are all examples of Lambda expressions. So hopefully by now you get a little feel for its syntax. But I'm sure the most important thing now is, well, okay, Raoul, it looks very nice and concise, but how do I actually make use of those Lambda expressions in my code base? And this is what we're going to look at now. But it's worth reflecting a little bit. In Java, you can use an expression where a type is expected. So I can pass an array list to a method because that method is expecting a list interface or an array list. I can pass an integer to a method because, well, it takes an integer as an argument. So we need to do the same exercise for Lambda expressions. What is the actual type of a Lambda expression? So the answer is, the type of Lambda expression is a functional interface. So this is a new terminology introduced in Java 8. And a functional interface is essentially an interface that declares exactly one method. So just one single method. And I've put abstract in brackets because interfaces in Java 8 can have default methods as well. And we'll talk about that towards the end of the webinar. So let's look at some example of what constitutes a functional interface. You're very familiar with the comparator interface. So it has just one single method called compare that takes two objects of type T. So it is a functional interface because it has only one single method. The runnable interface is also an example of a functional interface because it only defines a method run which returns void. The Apple predicate interface, which we described earlier, well, it turns out that was also a functional interface because it only defines a method called test. It doesn't define two of them, but only a single one. And that's what makes it a functional interface. So here comes probably the most difficult slide of the webinar. So I want you all to stay with me and read this carefully. So the signature of the method inside that functional interface essentially describes the signature of the Lambda expression. And what a Lambda expression lets you do is provide that implementation of the method from the interface directly inline. And the whole expression itself can be treated as an instance of the functional interface. So this is a bit like what we were doing using anonymous classes. So we can instantiate the interface directly inline by providing an implementation for its method. But using Lambda expressions, we don't have to care about the name of the method. We can just provide that implementation directly inline. So let's look at some example to really get an idea for this. So here we're using the runnable interface. So I have a method called process, very simple, that takes a runnable object as an argument and just executes that object. Here we're creating two ways to instantiate a runnable object. The first one, runnable R1, using a Lambda expression. So, well, the Lambda expression has no parameter and returns void. In this case, it just prints hello world 1. And the second way is to use the anonymous classes, which you've seen during the presentation. So here we, well, instantiate a runnable object and provide the implementation for the run method. And those two ways of doing things are very similar. It's just that with the Lambda expression, we're providing the implementation of the run method directly inline. We don't have to care about writing public void run. We don't have to worry about writing new runnable. So if I call process with the variable R1 and process with variable R2, then the output would be hello world 1 and hello world 2 because the two things are creating objects of type runnable. We can even pass the Lambda expressions directly to the process method. We don't have to store it into a variable. We could pass it directly as an argument. So that was the hardest part of the presentation. So now let's look at how we can apply this idea concretely. So I will discuss a pattern called the execute a run pattern. And this pattern is very frequent when you have to deal with resource handling. So it's very typical to write code that opens a resource, does something with that resource, and then closes the resource. For example, it might be opening a database, then getting information from the table, and finally closing this database. However, if you have to read from another table, typically what happens is that we duplicate this code of connecting to the database and closing it. Only the box in the middle, shown in red, matters. It's what you actually do with this resource. And that's why we call it execute around, because this processing code is surrounded by this kind of opening and closing code. So let's look concretely in code on what we can do with this. So here's an example on how to read from a file called data.txt. So we're creating a buffer reader from the file, and we're returning the first line. Well, this is nice code, but it's kind of limited. What if we'd like to read more things than just the first line of that file? What do? Do we copy-paste the method and just change it so it reads the next 2 lines? Or can we do something better? Well, ideally, what we'd like to do is, well, it's pass different behaviors to the process file method. So given a file, we'd like to do multiple things with it. But this method should kind of encapsulate the idea of opening and closing the file. So this is what this slide shows. We have a process file method, and we like to pass different Lambda expressions that convey how to process the file. So in the first case, we read the first line. In the second case, we'd like to concatenate the first 2 lines of the file. So how can we write this type of code? How can we gain that flexibility? Well, we're making use of Lambda expressions. If you remember, we can only use a Lambda expression in the context of a functional interface. So let's create a functional interface. Here, the interface is called buffered reader processor, and it declares one method called process that takes a buffer reader and returns a string and might throw an IO exception along the way. For example, if the file doesn't exist on the system. So we refactor our process file method to take as an argument this interface, buffer reader processor. So now what we can do is basically pass multiple different objects of type buffer reader processor, and those objects will encapsulate the different ways we like to process the file. Of course, we need to execute this processing. So here we say return p.processBr. So p is the buffer reader processor that is passed as an argument, and this will take the buffered reader. And because buffer reader processes a Lambda expression, now we can call process file with different ways of processing the file. So in the first case, we say, well, I'd like to read the first line, and please return it. In the second case, we say, well, read the first 2 lines and concatenate them and return the result. So the little exercise that we've done in 2 steps, we've managed to start from a method that was processing a file in a very specific way to writing a process file method that can now process the file in multiple different ways. But they all share the same code of opening and closing the resource. So the Java designers, they thought about us. There's no need to create our own functional interfaces every single time we like to use Lambda expressions. They provide us with a bunch of functional interface already out of the box. And these are available in the new package called java.util.function. And here are some examples of them. So there is a predicate interface that says, well, I'm a Lambda expression that takes an object of type t and returns a boolean. So this is similar to the Apple predicate we defined earlier, but it works on any type. There's a consumer interface that takes an object and returns void. There's a function interface that takes an object of type t and returns a result that might be of another type. So this is very useful, for example, when you want to extract information. So let's say you have a transaction and you'd like to return its value. So this would be a function that takes a transaction and returns an integer. There's also a supplier, which can be used to create objects. So this is similar to the factory design pattern, where you say, well, I'd like to create different objects of a unified type, and so on. There's no need to remember all those functional interfaces, but I just wanted to show you that there are some available outside the box, and you should look at them if you'd like to use Lambda expressions. Okay, so let's now talk about a second feature that Java 8 brings, which are method references. What method references lets you do is reuse an existing method definition and pass them just like Lambda expressions. I know it sounds a little bit abstract, so let's look at some example. Using Lambda expressions, we could say, well, take an apple and return its weight. But really all we're doing here is describing how to call the method getWeight on an apple object. Using method references, you could write the same code by saying apple : getWeight. Because really all you want to do is access the getWeight method. It's a bit pointless to describe a recipe for calling this method. You can just say, well, take the method straight away. Here's another example, slightly more complicated, that says, well, I'm a Lambda expressions that takes two arguments, a string and an index. And I'd like to return the substring at index I. While using method references, we could write this string : substring. So if you are trying to figure out how does it work, don't worry, there's a bunch of recipes that allows you to convert Lambda expressions into method references. And the benefit of method references is that they may make your code read more like the problem statement, and I will show some example in a moment. So there are three main recipes for creating method references. You can access them later after the presentations. So let's look at a little example of how we can apply method references. So let's start from the beginning. Let's say we have this inventory of apples and we like to compare them based on their weight. So previously, before Java 8, you might write code that looks like this. We'll create a class, Apple Comparator, that implements the comparator interface. This gives a method compare that takes two apples, and we're saying, well, take the weight of the first apple and compare it with the weight of the second apple. We are now able to instantiate a Apple Comparator object and pass it to the sort method. By the way, if you're wondering about why we're calling sort directly on the list interface, is because in Java 8 the list interface has been updated with sort method. Previously you'd have to do collections.sort. So this is an enhancement to the library. So let's look at step 2. How can we improve this code a little bit? Well, we've mentioned anonymous classes. So this allows us to declare and instantiate a comparator object directly in line without having to declare an extra class that we're not going to reuse anyway. So this is what this code does. But we've now seen how to use Lambda expressions, right? So comparator is a functional interface. So we can provide the implementation of the compare method directly inline. So here we're saying, well, given two apples, take the weight of the first one and compare it with the weight of the second one. So our code is starting to look a little bit better, but can we make it even nicer? Well, Java 8 has a little feature called type inference. It can infer the arguments of the Lambda expression. So instead of repeating apple A1 and apple A2, it can figure it out that, well, we're working with apples anyway because it's a list of apples, so you don't have to repeat those types. There's no rules on whether you should make use of type inference or not. Sometimes it may work well for code that is quite small. There's no need to repeat the type of the argument, but if you have really complex code, then it might be useful to have the types available for documentation. Let's use a little bit of a help from the library now. So there is a new comparing static method available in the comparator interface. And yes, I just said static method in an interface. So in Java 8, you can have static methods declared inside an interface. And what comparing does is it takes a key. So here we're saying, well, give an apple, returns the weight, and I will generate a comparator automatically for you. I will figure it out that what you want is to compare the integers that represent the weight of the apple. So we can rewrite our code this way, because by weight is a comparator object. This is what comparing is returning. So code is looking much more concise. This is awesome. Can we do even better? Well, I described method references earlier, and we can actually rewrite the previous Lambda expression. So taking an apple and returning its weight, by just passing the getWeight method directly to inline to the comparing. And this is what this code shows. We can go one step further by tidying things up. So here we're doing an import static of the comparator.comparing method. And finally, we can write a code as follows: inventory sort, comparing based on the weights of the apple. So this is really amazing because now our code reads like the problem statement. So it's much easier to maintain and is much more readable. So hopefully I've convinced you that Lambda expressions and method references combined with the idea of behavioral parameterization can make your code more flexible and more concise. So let's move on to the next part of the webinar, which is talking about the Streams API. So I'd like you to reflect a little bit. Imagine a world without collections. Imagine you never had access to a list or a set or an array. What would we do? Well, we wouldn't be able to write any sort of applications, right? Because most applications these days need some form of container. Let it be a list of transactions that you like to process, or a list of inputs to feed into some mathematical model, and so on. So collections are really fundamental to all code we write these days. Unfortunately, dealing with them is far from perfect. What if we want to have SQL-like operations on those collections? A database offers us operations such as grouping by or select or where. Why don't we have access to all of these in Java? And most importantly, how do you efficiently process large collections? So in the context of really large data, how are we going to process this collection in the most optimal way? This is very complicated. And this is what the Streams API is trying to tackle. First, SQL-like operations. It's very typical to process a collection and say, well, we'd like to find the transaction with the highest value in this collection of transactions. Or we might want to group a list of transactions based on some property. For example, transactions that are related to grocery, transactions that are related to internet shopping, and so on. And those types of patterns are re-implemented every single time. In SQL, we can do something much better, right? We can just say the query, so what we expect, but we don't really say how to implement the query. So here, for example, it's a SQL query that says, well, select the ID and the maximal value transaction from a table of transactions. But this query doesn't say how we have to implement that. It doesn't say that we have to iterate the collection of transactions. It could be done in parallel, but this is abstracted away. Here's how it impacts, how it relates to Java. So we take a list of transactions, and we say, well, we'd like to filter those transactions that are related to grocery. So we add those up to an accumulator. Next, we say, well, we'd like to sort all those transactions. So we implement a comparator by saying how to sort them. And finally, we say we'd like to extract the transaction IDs. Again, we implement the iteration logic by saying, well, for each element in this list, please extract the ID and add it to an accumulator. Using the Streams API, you no longer have to implement all those different patterns. You can actually mix them up. So in this code, we're saying, given a list of transactions, get me a stream view. So this is what the .stream method does. And then we have access to all those kind of nice operations. So here we say, well, filter the transactions that are related to grocery. Then we say, well, sort them based on their value. And here you can see this is the comparing static method we saw earlier, and it takes a method reference. So compare them based on the value. And then because this is a comparator object that is returned, we can call the reverse method, which is a new method on the comparator interface. Next, we say, well, we'd like to extract the transaction IDs, and this is what the map method does. It takes a method reference that says, well, given transaction, call the getID method and generate me a stream of that. And collect here says, well, given the stream, generate a list. And this is why the return result is a list of integer, because we've come from a list of transactions to a list of IDs. And now you're wondering, well, Raoul, you're giving me all this talk about processing collection very efficiently and in parallel and all of that. So how do you do it? Well, because we are able now to kind of abstract away how those operations are implemented, we can ask for a parallel stream instead of just a normal stream. And you can see in this code we're saying transaction.parallel stream, and then we're saying filter, sorted, map, collect. But behind the scene, this code will make use of your multi-core architectures, because the implementation details are abstracted away at the library level. So the implementation is abstracted away through the filter method, through the sorted method, and map. It might be done sequentially, so as a loop, but it might also be using a bunch of threads and splitting the work behind the scenes. But what's great is that this is all abstracted away for us. All right, so I'm talking about streams, but maybe let's take a step back and really define what a stream is. So there's two definitions to it. A more informal one, which is just, well, it's a fancy iterator with database-like operations, such as filter, grouping, and extracting. The more formal definition given in the Java API is a stream is a sequence of elements from a source that supports aggregate operations. So let's break down this definition a little bit. Sequence of elements. Well, a stream provides an interface to a sequence set of values of a specific type. For example, a source could be, a sequence of elements could be a list of integers. So a list of integers is a sequence of integer elements. But the streams don't actually store elements. They don't live in memory. They are computed on demand, and we'll see that in the next examples. A source, well, a stream can be computed from anything that returns data. So it could be a collection, it could be arrays, it could be files, so input-output resources, or even a database. And what does aggregate operations mean? Well, it's all those kind of SQL-like operations, such that are inspired from functional programming. So, filter, map, reducing, so combining the values in the source into a single value, finding an element, ensuring that all the elements match a given criteria, or sorting. All those methods are called aggregate operations. Streams have two additional properties that are worth keeping in mind. One is pipelining, which I've shown earlier with the concept of stream processing. So all those operations can be pipelined together to create a larger recipe. So you can create a pipeline of a message just like you can pipe Unix commands. And this style enables certain optimizations, which we'll discuss in a moment. Finally, the other property is a fancy terminology that comes up sometimes. It's internal iteration. So in contrast to collections, where you have to iterate the collection explicitly by pulling elements from it, using the Stream API, this iteration logic is pushed inside the library. So it's all done internally inside the method. And this is why we call this internal iteration as opposed to external iteration with collections. So let's illustrate those two ideas. So pipelining works like this. So there's two types of operations that a stream provides. Intermediate operations, which can be connected together, such as filter, sorted, and map, in the example that I've shown and illustrated below. And finally, terminal operations. So terminal operations are operations that actually compute a result in the pipeline. So essentially, you can connect all those intermediate operations together to create a nice pipeline that represents some data processing that you like to do. And as soon as you like to calculate this processing, then you call it terminal operations. And in this example, the terminal operation is collect. Here's one way to illustrate internal iteration. So you can see that with collections in the bottom of the diagram, we're pulling elements out of it, and those elements are pulled through an iterator, for example, using for each, and then you apply your code on each of those elements. But using internal iteration, we're passing a lambda which applies a behavior on each element inside the collection. So we don't have to worry about how to iterate all through this collection. This is all abstracted away to us. So it's all pushed within the library. This is one way to visualize stream processing. So given a source of transactions with different IDs and different values, first we like to filter this transaction based on the type and saying, well, I'd like to filter the transactions that are grocery transactions. Next, we'd like to sort them. Finally, we'd like to extract the IDs from this result. So this is why the result are circles, because it's another type, right? First, we're dealing with transaction. After the map operation, we're now dealing with integers. And finally, we're all collecting all of those elements generated inside a list of integers. So I mentioned earlier that streams enable some kinds of optimizations. And those optimizations are called laziness, loop fusion, and short-circuiting. It's not so important to know this terminology, but I'll show an example. So here, given a list of numbers from 1 to 8, we'd like to do some sort of mathematical processing. So we get a list of numbers. We get a stream out of it by calling the dot stream method. We say, well, we'd like to filter even numbers. Then we'd like to square them, so multiply them by themselves using the map method. Then we'd like to return the first two results, and finally generate a list from them. So there's several ways on how we could actually calculate this result. One way would be to process the whole list of numbers to figure out which ones are even. So this is done in the filter. Finally, the result of the filter could be passed to the map method that will square each of them. And then we're saying, well, actually, I'd just like to return the first two results. So this approach is a bit silly, right? Let's say we had a list of 10 million numbers, and all we want to do is return the first two numbers that are even and squared. There's no need to process this whole list. And this is what the Streams API lets you do. So here we take the same example, and there's an output of what happens behind the scene. So first we take the first number, which is 1, and filter figures out that, well, it's not an even number, so let's throw it away. Takes the next number, which is 2, figures out that, well, it's an even number. Well, it can pass it to the map method directly. So this is what we call this loop fusion, because filter and map have been fused together. You don't have to wait for the whole result of filter to start squaring the numbers. You can already pass it to it. So map takes the number 2 and returns a square. So that's going to be number 4. This is passed to limit, and limit figures out that, okay, well, we've calculated one number already, so there's only one left. We carry on. We come back to filter. The next number in the list is 3. Is 3 an even number? No, it's not. So we can throw it away right away. The next number is 4. Filter figures out that 4 is an even number. Great. Let's pass it to map directly. Map squares it, and the result is passed to limit. And then limit is happy, right? Because all it's asking is for 2 numbers. So the computation can stop, and we can move on. And this idea of stopping the computation as soon as we've got enough result is called short-circuiting. So you can notice that there's no need to process number 5, 6, 7, 8 in this list, because we've already calculated what we need. And those are the types of optimizations that the Streams API does behind the scene for you. It's able to merge all those operations together into one loop. All right, so you saw a couple of operations in those examples, but there's many more. There's a lot of methods available in the API. Here are some examples. So there's filter that you've seen. There's distinct that removes duplicate. There's limit and skip that allows you to truncate the result or ignore some elements. There's a bunch of operations to find elements that match a given criteria. There's map and flat map that allows you to extract information from objects or specify some transformations. There's reduce, which allows you to combine elements in a stream into one value. I won't go in details about those operations. I invite you to have a look at the Java API or the examples in our book. But there's much more that you can do with streams, and I'd like to give you a little taste for it. So let's look at this fairly complicated code. What it's trying to do is giving a menu, so a list of dishes. We like to create a map of a dish type to a list of dishes. So for example, we could have vegetarian dishes or meat dishes or fish dishes. So we're looping through all the elements in this menu. We get the type for a dish. Then we check our map to see, well, is there a list for this type of dishes already? If not, then, well, we need to create an array list for it. And then we can insert the dish in that map. Then we keep going for every single element, and we can build this nice map of dish type to a list of dishes. Using the Stream API, we can write this code in one line. All it's trying to do is, well, giving a list of dishes, we like to group them by type. And this code reads just like the problem statement. And behind the scene, the Streams API will figure out how to generate this map. So you can see in this diagram, we've got a stream. We're passing a classification function to it, which is the type of dishes. And then internally, it will figure out that, well, the dish type, it becomes the key of the map, and then I can start building some buckets to put all the elements that match a given dish type. So you can build really advanced data processing queries using the Streams API, and this is just a taste for it. You can also combine those types of operations together. So if you fancy having nested maps, then you can do that as well. For example, here we're saying, well, I like to produce a two-level map that says whether a dish is vegetarian or not, and then group them by the type. So the produce map is false, which means the key false means it's not a vegetarian meat dish. So we'll have fish, prawns, and salmon. Then we have dishes of type meat, pork, beef, and chicken. And then the key true is about dishes that are vegetarian. So those would be French fries, rice, seasoned fruit, pizza, and so on. So we've built a nested map. So the Streams API is a lot of fun, and you can build a lot of advanced queries. Now I'd like to move on to parallelization. So I discussed that streams, you know, they let you write code that magically parallelize behind the scene, magically use a multi-core. And it's not so easy in practice, and I'd like to describe a little story here. So let's say you need to calculate all the numbers between 1 and n. So 1 plus 2 plus 3 plus 4 plus 5 and so on until you reach the boundary n. So sequentially, you may write this code as follows. We have a result. We iterate through all those numbers and add them up. So that would produce a result. So I run that code with an argument n of 10 million, and that took 3 milliseconds to execute. So fairly fast. Let's use the Streams API to see if we can rewrite this code. So using the Stream API, we can say, well, stream iterate starting from 1, and then generate the next number. So 1 plus 1, which will be 2. The next time around, it will be 3, then 4, then 5, then 6, and so on. And we say that we like to get only the first n elements, so in this case 10 million, and finally sum them up. So this reduced long sum, all it means is combine all those numbers together and sum them up. That took 98 milliseconds to run on my machine. So this is about 30 times slower than the initial sequential version, right? So you might think, well, streams are useless. They're so slow. What if we use parallel stream? Because this is just using a sequential stream. Well, let's call .parallel on this. And maybe surprisingly, this is even slower. This executes at 193 milliseconds, so twice as slow as the sequential version. So you may be wondering, well, that doesn't seem very good. We've had all this talk about parallelization, but we've come from 3 milliseconds to 193 milliseconds. So what's up with that? Well, turns out we have to be a little bit careful about how we use streams. So in these previous versions, what happened is that all the numbers generated here are boxed. So instead of working with primitive numbers, we're working with an object of type integer, specifically here an object of type long. And the next thing to realize is that certain stream operations parallelize better than others. In this case, iterate is really a not very parallelizable method because the next element can only be calculated when you find out about the previous one. So I can calculate 2 when I know about 1. I can calculate 3 when I know about 2. So you need to generate all of this list before you can execute in a parallel. So to improve this code a little bit, there's another operation in the stream API called range closed. And that gives you a range of number available. And specifically those numbers are primitive types. So if we run this code, and this is a sequential execution again, that takes 17 milliseconds. So we've come from 98 to 17, so that's an improvement. So now let's call .parallel, and well, good news, this code now takes 1 millisecond to execute. And the reason is twofold. One is we're not working with boxed objects anymore, and the second is range closed is more parallelizable than iterate. Because we can create this range ahead of time, we can split it into different chunks that different CPUs will execute, and then finally combine those results. This sort of strategy is called the fork join framework. It's not so important to know about it for the purpose of this webinar, but the key takeaway is that if you want to write parallel code using the Streams API, you still have to be a bit careful about how you write your code. You have to worry about boxing, and you have to worry about whether the operation itself they're using are inherently parallelizable or not. But if you do, then it comes with benefits. Our code is now 3 times faster than our sequential version. There's much more to the Stream API. There's no time in this webinar to talk about it, but there's topics such as infinite streams that lets you build streams that calculate elements forever. There's the collectors, so these are the operations I showed earlier, such as grouping by. You can build really advanced queries using them. So I invite you to take a look at them in the API or in a book. I'd like now to move on to a different topic in Java 8, which is this new class called optional. And the optional class, its goal is it's twofold. One is to simplify how we deal with null checking. So how can we reduce null pointer exceptions? I'm sure a lot of you have dealt with null pointer exceptions before. If you tell me that you've never seen a null pointer exception, then I won't believe you. I'm sorry. But this is what optional does. It's very painful to deal with null pointer exceptions, and maybe there's a way to simplify that. So let's look at some example. So first, this is how we can create an optional object. So what it means is an object that may contain a value. So there's possibly one value or there isn't. And this is encapsulated through optional. So here we say, well, there are different ways to create optional objects. One is through the factory method of, that takes a not null argument. If the object passes an argument is null, then it throws an exception directly saying it's an illegal argument exception. So immediately we know that we've had a null reference. So let's look at some patterns. Typically, we write code as follows. If the transaction is not equal to null, then we could print it. Using this optional class, we can rewrite this code as follows. Given an optional transaction, if it's present, then we print it. And here we're making use of a method reference because we're saying, well, given the value, he would like to print it. But we could pass different behaviors to execute on that optional value. Another pattern is rejecting certain values. So for example, if you want to ensure that a transaction has an ID greater than 10, then you write code as follows. If transaction is not equal to null and transaction.getID is greater than 10, then print it. Using the optional class, we can rewrite it as follows. We can filter the transaction, making sure that its ID is greater than 10, and if it is, then we can print it. Here's another bit more involved pattern. We like to transform a value if it's present. So let's come back to the transaction example. So if transaction is not equal to null, then we like to get its group. and then we want to make sure that the group is equal to shopping, and then we print it. And I'd like you to notice that this code is slightly a bit smarter. We could have said group.equals shopping, but if we had done that, then we'd have to check that group is also not null before we can check whether it's equals to null to shopping. Using the optional class, we can write this code as follows. We say, given an optional object, well, extract the group from it, then make sure that it's equal to shopping, and finally, if all those conditions are still holding, then we can print it. So this is a more declarative way to deal with the presence or absence of a value. But what's really great is that all of those methods are accessible through the optional object. So you're forced to check whether the value is present or not. But if you just get a variable such as transaction, you may forget to check whether it's null or not. And this is when you get null pointer exceptions. With an optional object, this is not possible. You always have to check whether it may or not contain a value. Here's another use case, the default values. So instead of writing code as follows, if the list is not equal to null, then we return its size, otherwise we return -1. We can write it as follows using an optional object. First, extract the size. Well, if we couldn't do that, then we can provide a default value using the OS method. Here's a little bit more complicated example, and I just want you guys to see what you can do using optional. You don't need to understand this code specifically, but here, we'd like to extract a nested structure from a transaction. So if the transaction is null, we return a default value. Then we'd like to extract the destinator from that transaction. And if destinator is null, then we need to return a default value as well, unknown. Now we can extract the country from the destinator, but we need to check if the country is null as well. So we return a default value if it's null. Finally, we'd like to return the name of this country, but we also need to check if that's null. If it's not, then we return the name, otherwise we return a null. So just to write a simple code, which is given transaction, return the name of the country, we already have to write about 12 lines of code that involves null checking. This is very painful, and this affects the readability of your code. Using optional, you can rewrite this code as follows by saying, well, given transaction, extract the destinator, then extract the country, and then finally return the name. And if any of those guys are null, then return the default value straight away, unknown. So this code is more readable. We can figure out that, well, we want to do some extraction and return a default value. But what's most important is that we can't forget to check whether this is null, because this is encapsulated through the optional class methods. So finally, I'd like to talk about another feature of Java 8 called default methods. So now, in a nutshell, it's a very easy way to describe it, is that interfaces can have implementation code, just like classes. So if you look at the list interface in Java 8, you'll find default void sort that takes a comparator and then just call collections.sort. So this is the method we've been using all along during the webinar, and this is how it's implemented. So you may be wondering, wait a minute, how is that even possible? Interfaces are all about declaring contract. Why can we have implementation code inside them now? Well, it turns out there's a specific use case, right? Adding a method to an interface is a major problem from a library designing point of view. Because now all implementers of your API needs to support this method. So let's say you're providing me with an interface and I'm implementing it, and tomorrow you're creating this new method, then suddenly if I recompile my project, I'll get compile errors because my classes are not supporting the new contract of the interface. They're not providing an implementation for that new method you've introduced. So the general idea is, well, to evolve libraries in a backward compatible way, what library designers have to do is provide a default implementation that you can inherit from. So if you're not providing it, there's one accessible. So let's visualize this a little bit. So let's say we have interface API version 1, and a user is implementing it. So those empty boxes represent methods to support, and the box full represent implementations. In API version 2, you decide that, well, the API will really benefit from introducing this new method. So in this case, it's this red empty square. However, this is problematic for all your implementers because they now need to provide an implementation for it. The interface does not, the contract of the interface does not hold anymore. So what you can do is, well, push the implementation directly in the interface, and now your users can inherit from it. So users don't have to modify the classes to implement this new method. They will get it automatically from the interface. So what are applications of default methods? Well, one of them is optional methods. So a big pain with iterators in Java, with the iterate interface, is that it has a remove method. But often what happens in real world is that when we implement the iterator interface, we really do not care about this remove method. We only care about has next and next. Unfortunately, to make the contract of the interface happy, we have to provide an implementation. So often it's a default implementation. So just a remove method with an empty block. Using default methods, we can now provide a default implementation. So in the case of Java 8, this provides a unsupported operation exception. So now, when you implement an iterator, you don't have to provide implementation from remove anymore. It's automatically inherited. Another use case of default methods are multiple inheritance. So Java is introducing a form of multiple inheritance. And multiple inheritance is very famous in C++. And if you're worrying about some details such as the diamond operator, stay with me. We'll talk about them in the next few minutes. But I'd like you to realize that, well, we've been able to implement multiple interfaces from day one. So if you look at the array list class definition, it extends an abstract list, but implements several interfaces. It implements a list, it implements random access, clonable, serializable, iterable, and so on. So we've had multiple inheritance of types for a long time. But the picture is changed a little bit because now we have a model where interfaces can have default implementations, right? So on the left-hand side, you can see the single inheritance model where a class can inherit functionality from only one place. But now in Java 8, a class can inherit multiple functionalities from multiple interfaces. So what are applications of this? Well, let's look through a use case. Let's say you would like to define your own sort of collection API at work. So you're creating a size interface that says that a given class needs to support a size method. And we can now provide a default implementation for isEmpty. It's just calling, well, does the size method return 0? So we get this implementation for free. Whoever is implementing the size interface will have access to the isEmpty method out of the box, provided it gives an implementation for the method size. Next, we can define another interface for reachable that defines a method for each to execute a piece of functionality on each element of a list. We can also define another interface called removable that defines a method removeIf, which takes a condition, and if the condition match, then it removes an element from the iterator. You don't need to worry about all the details of this code, but we've got different interfaces. We've got sized, removable, and for reachable that all provide default implementations. So now we can start to mix those guys up together. We can create a bag collection that is just removable and for reachable. And the bag class will have the default implementation of removeIf and for each. We could create another sort of container, for example box, that can be for reachable or sized. So this is great because we can reuse the same functionality across different classes. So box and bag both share the functionality for reachable because it defines a default method for each. So I can already hear in the background some people wondering about methods. What if we implement two interfaces that have the same method name and they both provide an implementation for it, then what do we do? Well, there's different resolution rules to deal with potential conflicts. There's essentially two rules. One is class always wins. So if you're extending from a class and a class provides a method, then this takes priority, whatever the circumstances. Otherwise, if there's conflicts between several interfaces declaring the same method name and signature, then the most specific one is selected. So this sounds a little bit abstract. Let's look at some examples to get a feel for it. Here's the first use case. We've got a class C that implements an interface, B, providing a default implementation for hello. And this interface B is extending the interface A itself. That also defines a default method called hello. So in code, it looks like this. Can you guess what the output of the program will be? So if I instantiate an object of type C and call the method hello, what will get printed? Well, because B is more specific than A, in fact the interface B extends A, then this code will print hello from B because the default method hello has priority inside the interface B. So this is not a problem. What more complicated the use case? What if now we introduce a class D that C extends from? D implements A, and B also extends the interface A. What do you think gets printed? Well, if you send a hello from A, there's a little trick to it. In fact, the class D doesn't actually provide an implementation for the method hello. Only B provides one. So B is still the most specific one. So this code will print hello from B. However, if we modify this example, so D provides a direct implementation of the method hello, then because classes have priority, then this code will print hello from D. So this is the real tricky example. What if we've got two interfaces, A and B, and there's no relationship between those two, and they both provide a default method called hello? What can we do? Well, turns out there's not much we can do, so the compiler will throw an error, and you'll have to deal with this explicitly. You'll have to decide which method you want to call. So you can override the method hello in the class C, and decide to either call the one from A or the one from B. So this is a new syntax here. b.super.hello says, I like to call the method hello from the interface B. So whenever you've got conflicts, you can always explicitly disambiguate them. And that's the good news. We don't have those silly C++ issues where it's tricky to understand exactly which method we're inheriting from. So here's the final use case, which is known as the diamond problem. The reason why it's called a diamond problem is because if you look at the structure, it almost looks like a diamond. So we've got a class D that implements both interface B and C. And those two interfaces are extending the interface A that provides a default method called hello. Well, since there's only one method we inherit from, this code will always get the one from A because C and B do not provide any implementation. If B was providing an implementation, then D would inherit this one because B is more specific than A. If C on top of that was also providing its own implementation, then we'd have to explicitly disambiguate the code. Right, so we've reached the end of this webinar. I've described lambdas, method references, streams, default methods, optional. So there's a lot of material to understand, and there's a lot more actually to Java 8. There's this new class called Completable Future that allows you to do asynchronous programming in the style of the Streams API, where you can describe recipes and how to compute some data, but in an asynchronous way. There's more to performance. We've had iterators. We now have also splitterators, which describes how to iterate a collection in parallel. There's many recipes to make use of the optional class. Testing, debugging, and tooling will be changed because we now have to deal with Lambda Expressions and streams. All those features lets you embrace a little bit more functional programming in Java. And You can find all of this information in our book. There's a 38% discount code displayed here. So it's about 400 pages book. So it will take some time to read, but by the end of it, hopefully you'll be a Java 8 expert. So thank you for listening to the webinar today. I'd like to thank eSynergy Solutions again to organize this. And if you have any questions, please leave them in the chat box, and I will address them. Thank you. So the first question is it possible to use curring in Java 8? And the answer is that yes, you can. You can't do it in a very nice way like you can in Haskell and Scala, but you can create a method that returns the Lambda expressions. So in our book we describe, actually, we have 2 functional programming chapters that describe functional programming techniques, and we describe how to do curring in Java 8. Another question is, were some of the features inspired by Guava, or were Google directly involved? And the answer is yes. There was an expert group that has taken design decisions from Guava, and all those design decisions and discussions are publicly available on the Java 8 Lambda mailing list. Another question is, would the stream versions still be faster without parallel? So I addressed that in the previous example. So the parallel stream version would be execute faster, but that does not mean that every time you call a dot parallel on a stream that it will actually execute faster. There are many parameters to keep in mind. One is the size of the stream. So if you have a small stream, then chances are executing it in sequentially would be faster, because using a parallel stream has a bunch of overhead as well. We need to split the task into multiple tasks. We need to execute them in different threads and combine the results. So there are some trade-offs. We discussed those trade-offs in chapter 6 of the book, so I invite you to have a look at that. There's another question. Do the features described encourage a move away from implementing behavior in domain objects towards a domain model where functions are defined outside by orchestrating code using the domain's objects accessible? This person, please be useful if you could rephrase the question a little bit. But yes, Java 8 encourages a style of behavior parameterization, and I think that's what the question is asking for. And some more questions coming. Awesome, guys, keep them coming. I love questions. Please email the slides to all the attendees. Yes, I will email all the slides to the attendees, and Adil Green and eSynergy Solution will follow up about that. Another question is, do we have case classes? We do not have case classes. So case classes is a feature from Scala. This is not coming to Java yet, but it might maybe one day in Java 9 or Java 10. In our book, we describe a way to have a sort of case classes in Java 8, so I'd invite you to have a look at it. Where can our slides be downloaded for references? So eSynergy Solutions will follow up and send that to you guys. Another question is JVM tuning going to be different in Java 8? Well, not really, because the idea of parallel streams is that you don't have to worry about tuning. The JVM behind the scenes can figure that out. So specifically, the parallel streams are making use of the fork join thread pool, if you're familiar with it. This is kind of configurable, but it's not recommended. The next question is, how testable is the code with the new Java 8 paradigm? There are different recipes that you can follow to test Lambda expressions. Again, they're described in a book. We have a chapter dedicated to testing and debugging and refactoring. So I invite you to have a look at it, or feel free to contact me directly. Will it be easy to migrate from Java 6 to Java 8? The answer depends really on your code base. I mean, there are some backward incompatibilities between Java 6, Java 7, and Java 8. So you'd want to ensure that these do not happen. But there are already some refactoring tools that allow you to convert some code written in previous version of Java to using Java 8 features. All right, guys, I'm getting many questions. Please keep them coming. They're really great. Is there any change to the thread class in Java 8? There are no changes to the thread class in Java 8, but there are some concurrency updates to the package java.util.concurrent. They're also described in the books. I recommend having a look. Java 8 has backward compatibility. I mean, if I just upgrade my Java 7 to Java 8, my application still work, even though I don't use any Java 8 features. The answer is there are some minor backward compatibility which only affects some very, very, very specific use cases. So in 99.999% of the cases, you should be fine to migrate your code. The next question is, when will Java 8 be supported in production? So Java 8 has already been released in March, and it's available to download, so it is supported in production. And is Java 8 production ready? Well, I'm going to say yes to that, but you know, since the release of Java 8 in March, there was already a new updates to it. Next question. So here was the question about the domain model. So to rephrase, I was wondering if the features encourage definition of domain classes that just have attributes with getters and setters, rather than a behavioral interface. It seems like the feature encourages that approach where the behavior is defined outside the domain. Yes. Yes, there's not many ways to answer that question, but I really like the way you're saying that encourage defining domain classes that only have getters and setters. And I'm even going to say that it encourages domain classes that only have getters, because Java 8 is a shift towards functional programming features, so we like to embrace more immutable objects. So definitely yes. We can avoid a new pointer exception, so I think this question is truncated. I can't really answer it. Do you know whether Eclipse provide auto suggestion for Lambda Expressions Java 8 APIs? I've been using IntelliJ and NetBeans. I know the support for them are really great. I know some people that have been using Eclipse, but the support is a little bit behind at the moment. But I think auto-completion is fine, because I've given many workshops where the attendees were making use of Eclipse and they had no problems. Yeah, someone is saying, talking about permanent generation exception, out of permgen exception. Yes, so this is not a Java 8 language feature, but more of a JDK 8 feature. So the perm generation space has been removed, so you won't come across those out of permgen exceptions. Well, lots of questions. Next one is, can we consider that the possibility to add method with body in an interface means that there's now a true multiple inheritance in Java? This is a very interesting question, and there's two sides to the story. Language designers, so the people in charge of Java, hate to think about it as Java has multiple inheritance. They're really seeing default methods as a tool to evolve libraries. But what language designers think and what we are going to do as developers is a different story. So definitely default methods can be used as a flexible inheritance mechanism. And now whether it's true multiple inheritance really depends on how do you define true multiple inheritance? Is it inheritance like in C++, or is it what Scala provides with traits, or even PHP, you know, Python and so on? So this is more of a philosophical question, I believe. Yeah, so are there any updates to the Java SQL API in Java 8, particularly with relation to Lambda syntax? I'm not aware of any updates to the SQL API in Java 8, but many frameworks that deal with databases will be updated to provide Lambda expressions. And the key idea, the key takeaway is that if you want Lambda expressions in your code base, you should start embracing functional interfaces. I don't have any more questions. I'm happy to take a couple more questions if there are. Otherwise, eSynergy solution will send the slides. I invite all of you to have a look at a book where you'll find all the juicy information. It's the most it's the reference about Java 8, most complete book on Java 8 on the market. Right, there's no more questions, so I'd like to thank everyone for coming to the webinar. Feel free to contact eSynergy Solutions and myself directly, and eSynergy Solution will follow up with the slides. Thank you, everyone.